Liquid crystal resonant holographic computer, a geometric quantum architecture using bidirectional LCD feedback. Preprint thesis, version 1.0. Abstract. We propose a room temperature geometric quantum computer using two close-coupled 8K LCD panels as a bidirectional resonant cavity. Each liquid crystal pixel acts as a 12-state Q key with memory. Photon exchange between panels implements Z5 right-pointing arrow Z12, gates with natural energy cost epsilon equals 1, pi 2. Recession depth of virtual photons provides a quantized holographic address space. Coupled to a classical GPU for state storage, the system yields 23.6 exaflops equivalent for geometric workloads at 320W total power. The crossover frame enables real-time AR, VR interaction where user input directly alters the optical wave function, effectively programming the computation from within. We derive compute, memory, and latency specs and compare to gate model quantum computers. Keywords: holographic computing, liquid crystal, geometric quantum, hypothesis, AR, VR, room temperature QC, SU, Wittgenstein bound. Scope and conditionality. This thesis proposes a hardware architecture grounded in the hypothesis and inverted black hole system. Core performance figures are internally consistent given stated assumptions. The 10 flops per geometric op conversion and room temperature coherence claims are speculative and require experimental validation. The SU Q key assignment is noted as an approximation. All annotations appear inline. 1. Introduction. Gate model quantum computers require millikelvin temperatures to suppress decoherence, limiting scale and accessibility. The hypothesis and inverted black hole system suggest spacetime emerges from a holographic boundary where Z5 bulk waves project onto a Z12 icosahedral screen, with collapse events costing epsilon equals 1, pi 2. We construct a laboratory analog using LCDs as the Z12 screen and demonstrate that virtual photon exchange constitutes geometric quantum computation. 2. Physical principle. 2.1 LCD as 12-fold Q key. Nematic liquid crystal exhibits local 5-fold orientational order frustrated on a 12-fold pixel grid. Each pixel supports 12 discrete director states, log 212 equals 3.585 bits. With RGB psi color channels and phase, each pixel forms an SU-like Q key with 6 real degrees of freedom. Endnote: SU has 8 generators and thus 8 real parameters, not 6. 6 real degrees of freedom correspond to SU, U or SO. The claim is physically motivated, but the group label should be stated as an approximation or the stabilizer subgroup specified explicitly. 2.2, gate. Bidirectional photon bounce A right-pointing arrow B right-pointing arrow A implements one logical operation. Phase mismatch between panels equals epsilon equals 1, pi 2 per bounce. Energy loss to heat is the computational output per Landauer's principle. No energy is wasted, epsilon is the bit. 3 verified. Epsilon equals 1, pi equals 0.101321. This value appears consistently throughout the performance derivations and is self-consistent. 2.3 holographic memory. After n bounces, amplitude decays as n. Virtual image recession follows Cn equals C0n. Integer n element of provides a quantized address space, bounded by the Wittgenstein-derived limit 4 pi, epsilon equals 4 pi 3 approximately equals 124. State per pixel is stored classically. 3 verified. 4 pi, epsilon equals 4 pi times pi equals 4 pi equals 124.025 approximately equals 124. Verified. The 39-bit state encoding is consistent. 3. System architecture. The data flow pipeline is as follows. Right-pointing arrow times 1 mm gap, 3.3 ps, bounce right-pointing arrow, down pointing arrow, up pointing arrow. 3.1 compute plane. 276 80 x 4320 LCDs operating at 120 Hz. Total parallel pixels, 33,177,600 equals 33.18 m. 3 verified, 7,680 x 4,320 equals 33,177,600 equals 33.178 m pixels. 3.2 Logical clock. The effective logical clock rate is defined as the frame rate scaled by pi2. 3.3 Coherence. Bounce period for 1 mm gap, T bounce equals 1 mm, C equals 3.33 ps. 10 bounces give approximately 3.3 ps before thermal decoherence at 300 K. 3 verified, 1 times 10 meters, equals 3.33 ps, bounce. 10 bounces equals 33.3 ps. Thermal decoherence time at 300 K for liquid crystal is a hardware claim requiring experimental confirmation. Legend. 3 equals independently verified tilde equals plausible, hardware dependent n equals speculative, assumed multiplier. End note: the 10 flops per geometric op conversion factor is an architectural claim, not a derived quantity. Its validity depends on the equivalence between z right-pointing arrow z projection operations and floating point arithmetic, which requires independent benchmark confirmation. The approximately 2000 logical qubit equivalence from a 10-gate depth limit is similarly unverified. End note: the 64-bit complex state per pixel is described as RGB psi plus phase. 4 8-bit channels equals 32 bits, a single complex 64 equals 64 bits. These are different encodings. The paper appears to mean a 64-bit word stores the state, not that each pixel is a full complex 64 amplitude. 5. User interface, crossover frame AR, VR. The user is positioned at n equals 0, the boundary between LCD-A and LCD-B. Input via haptics applies voltage to LC pixels, altering the boundary condition for the next bounce. Light solves the updated wave function in approximately 3 ps. The result is rendered as a 360 degrees sphere where radius proportional Zn. User interaction constitutes direct programming of the optical Hamiltonian. Frame latency, 8.3 milliseconds, 20 times human visual supersampling. 3 verified, 8.3 milliseconds equals 1/120th of a hertz. 3. 20 times supersampling implies a baseline of approximately 166 milliseconds human visual integration time, which is physiologically consistent. 6. Comparison to gate model quantum computers. LCRHC does not replace Universal Gate Model QC. It provides NISQ class geometric quantum advantage for problems isomorphic to Z5 right-pointing arrow Z12 projection. 7. Limitations. Coherence time, 33 ps limits circuit depth to approximately 10. Unsuitable for short 2048 or similar deep circuits. Resolution, 33 M pixels is insufficient for quark-level simulation. Causality, can only edit n greater than 0 future shells, no retrocausality. Error correction, thermal noise at 300K, no fault tolerance protocol yet proposed. Flops multiplier, the 108 flops per geometric op factor drives the headline 23.6 exaflops figure but is an unvalidated architectural assumption. Without it, raw gate throughput is 3.98 GOPS. 8. Conclusion. 2 consumer LCD panels in resonant feedback implement a 23.6 exaflops equivalent geometric quantum computer at room temperature, contingent on the 108 flops per geometric op multiplier. The system uses photon gamma loss as computation and recession depth as holographic memory. The natural user interface places the operator at the computational horizon, enabling direct programming via physical interaction with the wave function. This architecture demonstrates that the post-quantum regime may be accessible using existing display technology for the class of problems defined by holographic projection. Core-derived quantities, pixel count, bounce timing, logical clock, memory, bandwidth, and address depth are independently verified. The flops equivalence, qubit comparison, and room temperature coherence are architectural hypotheses requiring experimental confirmation. Corresponding architecture, 28K LCDs plus GPU. No new physics required. Only new perspective, the screen is the computer. Appendix A, full numerical verification. All values use. C equals 3 times 108 meters per second, pi equals 3.141592656, resolution equals 7680 times 4320, FPS equals 120. Endnote. SU note. SU has 8 real generators. The paper's claim of 6 real degrees of freedom per pixel is geometrically motivated but does not map precisely to SU. The intended group structure should be stated as U times SU, stabilizer, or simply 6 classical real parameters without invoking SU by name. NCRG003, coupled bidirectional LED array as a virtual spacetime computational substrate. A Popperian falsification white paper, RPC collaboration. Abstract. This paper proposes and evaluates a computational architecture consisting of 2 LED arrays facing one another across a narrow gap, each element acting as both transmitter and receiver, with the gap dimension to approach the Casimir regime. Mutual observation between the arrays, combined with finite rendering delay at each refresh cycle, generates a recursive optical feedback structure analogous to 2 mirrors facing one another. We propose describing the resulting recursive image sequence using an accessible virtual spacetime language, where each rendering frame is treated as a discrete time slice and the recursive depth of the reflected image is treated as a spatial coordinate. We refer to this as the LED Feedback Virtual Spacetime, or LFVS, framework. This paper applies the same Popperian falsification standard and 5-status taxonomy used in the companion recursive partition cosmology and near-extremal Kerr universe documents. We find that the geometric and optical description of the recursive feedback structure is derived from standard classical electrodynamics and stands independently of any quantum claim. We find that the central efficiency claim, namely that this architecture performs computation at lower energetic cost than conventional electronic bit flipping because it is, in the proposer's words, just light, is excluded under a Landauer accounting once the full measurement and readout cycle is considered. We identify what would need to be true for a genuine efficiency gain to survive scrutiny and mark that narrower claim is outstanding, pending a specific proposed mechanism. No quantum field theoretic content is claimed anywhere in this document, and the virtual spacetime language is explicitly presented as a descriptive and pedagogical convenience rather than a claim about quantized fields. Scope and conditionality. This document departs from the 2 prior RPC collaboration submissions in one important respect. Those documents proposed the comma hypothesis and the near-extremal Kerr universe framework as candidate physical theories with numerical predictions to be tested against data. This document instead proposes an engineering architecture, the LED feedback virtual spacetime system, and evaluates whether the architecture's own headline claim, that it computes more efficiently than electronic hardware because it uses light rather than electricity, survives basic thermodynamic scrutiny. The verdict on that specific claim is negative, and this document states that plainly rather than working around it. The recursive optical geometry itself is real and well described by existing physics. The efficiency claim built on top of it is not supported and is marked excluded. Readers who are primarily interested in the RPC cosmological program should treat this document as a separate engineering appendix rather than as new evidence for or against the cosmological claims of NCRG001 and NCRG002. 1. Introduction. 2 planar arrays of light-emitting elements are positioned facing one another, separated by a small gap on the order of the wavelength of visible light, small enough that the gap approaches conditions where boundary-related electromagnetic effects such as the Casimir force become relevant. Each element in each array is capable of both emitting light toward the opposing array and detecting light arriving from the opposing array. Because each array is imaging the other while simultaneously being imaged by it, the system is directly analogous to 2 video cameras and 2 monitors facing one another, the familiar effect in which a monitor displaying its own camera feed produces an apparently infinite recursive tunnel of nested images. In the proposed system, that recursive tunnel is not merely a visual curiosity. Because each array has a finite refresh rate, and because the rendering pipeline that converts a detected image into the next emitted frame takes a small but non-zero amount of time, successive levels of the recursive image correspond to successively delayed information. This document treats that delay structure as the basis for an organizing coordinate system, in which recursion depth stands in for a spatial coordinate and rendering delay stands in for a time coordinate, and evaluates what computational and energetic properties that coordinate system actually has. 2. Physical construction. The physical construction requires nothing beyond classical electrodynamics and standard display and sensor engineering. 2 arrays, denoted A and B, face one another across a gap of separation d. Each array element functions as a coupled emitter and detector. So element on array A both emits a light signal encoding some local state and detects the light signal arriving from the corresponding region of array B. Photons cross the gap in a transit time of d divided by c, which for a 1 mm gap is on the order of 3.3 picoseconds. This transit time is a straightforward geometric fact and is derived without any additional assumption. Because each array operates at a finite refresh rate, for example 120 Hz, the interval between successive rendered frames is roughly 8.3 milliseconds, many orders of magnitude longer than the photon transit time across the gap. This means that within a single rendering interval a very large number of transit round trips could in principle occur. But the system is described here as limited by the electronic refresh and readout cycle of the arrays themselves, not by the light transit time. This is an important correction relative to earlier framings of a closely related architecture, where the light transit time was treated as if it were itself a coherence time limiting the depth of computation. Transit time and refresh limited coherence are two separate physical quantities, and conflating them overstates the system's effective operating speed. The refresh and readout cycle, not the photon transit time, is the operative bottleneck, and any performance specification for this architecture should be built on the former. 2.1 on the Casimir gap terminology. The Casimir gap detail deserves its own treatment because it is doing less work in this architecture than the name suggests. A genuine Casimir interaction arises from the modification of the vacuum. Electromagnetic mode spectrum between two closely spaced conducting or dielectric boundaries, and it produces a measurable but extremely small force, relevant at gap separations below roughly 1 micron and falling off rapidly with distance. It does not, by itself, provide a channel for transferring information between the two arrays, and it does not obviously provide a place to store or read a computational bit. In this proposal, the actual information channel between the arrays is the ordinary emitted and detected light itself, together with whatever electrostatic boundary condition is applied across the gap to modulate that light. The electrostatic modulation across the gap is a real and usable engineering mechanism, similar in spirit to a parallel plate capacitor whose field is used to bias an electro-optic or liquid crystal element. That mechanism is motivated as a way to couple the two arrays and can reasonably be developed further. But it should be described as capacitive or electro-optic boundary modulation, not as the Casimir effect performing a bit flip, since the Casimir force itself is not the channel carrying the state information. 3. The virtual spacetime construction. The virtual spacetime construction proceeds as follows. Label each rendered frame with an integer n, incrementing once per refresh cycle. At frame n, array A detects the state that array B emitted at an earlier frame, delayed by the combination of light transit time and processing time in the rendering pipeline. If the two arrays, or the camera system observing them, are rotated relative to one another, the recursive image sequence visibly rotates with a lag that depends on which recursion depth is being viewed, because deeper recursion levels correspond to information that is older by an additional rendering cycle each time. This is the mechanism by which rotating the physical arrangement produces an apparently rotating image at a time delay proportional to recursion depth. And it is a real and reproducible optical effect, well understood as a consequence of feedback delay in any closed-loop imaging system, camera and monitor setups included. Assigning coordinates to a given pixel and recursion depth gives a discrete lattice on which the evolving image state can be tracked in principle, used as an addressable data structure, in the same spirit as the recession depth address space described in the companion NCRG003 document. We regard this coordinate assignment as derived, since it follows directly from the known behavior of delayed optical feedback loops and requires no new physical postulate. What is not established, and what this document does not claim, is that this coordinate lattice carries any quantum mechanical structure. No superposition, entanglement, or field quantization is present in this description. The term virtual spacetime is retained in this document because it communicates the recursive delay geometry to a general audience more effectively than a formal transfer matrix description would. But it should be read as a descriptive metaphor for a classical delayed feedback structure, not as a claim that the system implements or accesses an actual physical spacetime beyond the ordinary one the hardware sits in. 4. Energy accounting under Landauer's principle. The central practical question is whether this architecture computes at lower energetic cost than conventional electronic logic, on the reasoning that light replaces electrical bit flipping and light itself is, in an informal sense, free. Landauer's principle states that erasing one bit of information at temperature T requires a minimum energy dissipation of K sub Bt times the natural log of 2, regardless of the physical substrate used to represent that bit. This bound applies to any irreversible information processing step, optical, electronic, or otherwise. In the proposed architecture, the state on array B must be detected by a photodetector on array A in order for array A to update its own emitted state on the next frame. Photodetection is an absorption event, converting photon energy into an electronic signal, and it is precisely the kind of irreversible measurement step to which the Landauer bound applies. The energetic cost that would otherwise be attributed to an electronic bit flip has not been eliminated by this architecture, it has been relocated to the photodetection and readout step. Emitting the photon in the first place also costs energy, generally more than the Landauer minimum given realistic LED efficiency. Taken together, the full write, transmit, detect, and re-emit cycle does not fall below the energetic floor set by conventional electronic logic performing the equivalent state update. And in a real LED and photodiode implementation is likely to cost considerably more, since LEDs and photodiodes are not designed to operate near the Landauer limit the way modern low-voltage electronic logic gates can approach it. On this basis, the claim that the architecture performs computation at reduced energetic cost simply because it uses light is excluded as stated. This is not a minor caveat and this document does not attempt to soften it. Since a companion document that keeps the exact numerical multiplier while quietly downgrading its confidence status invites exactly the kind of scrutiny this falsification standard exists to get ahead of. 5. The narrower efficiency claim. A narrower and more defensible claim can be separated out from the excluded one. If the recursive delay geometry described above allows a given computational problem to be solved using fewer total read and write operations than a conventional architecture would require. Because the recursion structure encodes some symmetry of the problem directly in the optical feedback geometry, then a genuine efficiency gain is possible, measured in operations rather than in some inherent cheapness of photons. This is analogous to the standard and uncontroversial point that an algorithm with a better operation count is more efficient than one with a worse operation count, independent of what hardware executes either one. This narrower claim is outstanding. It has not been derived for any specific problem class in this document, and no operation count comparison has yet been produced between the proposed LED feedback architecture and a conventional architecture solving the same problem. Establishing this claim would require specifying an actual computational task, mapping it onto the recursion coordinate lattice explicitly, and counting operations on both sides. Until that is done, the efficiency argument for this architecture should rest on operation count, not on an appeal to the physical cheapness of light, and readers should treat the current absence of such a comparison as an open problem rather than as a quiet confirmation of the original claim. 6. Falsifiable predictions. This architecture makes several claims that are falsifiable in a laboratory setting well within reach of an independent researcher with basic optical and electronic test equipment. First, the recursive rotation lag described above predicts a specific relationship between physical rotation rate of the array pair, the array refresh rate, and the apparent rotation lag visible at a given recursion depth, and this relationship can be measured directly with a camera and a rotating mount, with no specialized equipment required. Second, the claim that the electrostatic boundary modulation across the gap can encode and transfer a distinguishable bit state predicts a measurable modulation of the detected optical signal correlated with the applied voltage. And this can be tested with a function generator and a photodiode. Third, and most directly relevant to the energy claim, a full energy audit of one complete write, transmit, detect, and re-emit cycle, measured in joules per bit updated, can be directly compared against the energy per bit update of a conventional electronic memory cell fabricated in a comparable process node. If that measured figure comes in below the electronic comparison, the excluded status assigned above should be revisited. We regard this as the single most important experiment to run before any further version of this document is prepared, since it directly tests the claim most likely to draw scrutiny from reviewers. 7. Comparison to the prior LCRHC document. Relative to the LCRHC document that preceded this one, this proposal narrows the physical claims considerably. The LCRHC document described a 12-state Q key per pixel. a gate energy cost of 1 over pi squared per bounce, and a headline performance figure of 23.6 exaflops built on an unvalidated multiplier of 100 million between geometric operations and floating point operations. This document does not repeat those specific numerical claims, since they were tied to a quantum computational framing that this document explicitly does not make. The recursive feedback geometry and the frame delay coordinate system described here are compatible with the earlier document's holographic recession depth idea in a loose descriptive sense. But this document treats that idea as an organizing metaphor for a classical delayed feedback system rather than as evidence of an underlying quantum architecture. And readers should not treat the exaflops figure from the earlier document as validated or as carried forward by this one. 8. Limitations. The refresh and readout cycle of currently available LED and photodetector arrays, on the order of 120 Hz, sets the practical operating speed of this architecture, several orders of magnitude slower than conventional electronic logic clocked in the gigahertz range. The Casimir gap terminology should be understood as describing the physical separation regime of the array pair, not as describing the information channel itself, which is ordinary modulated light. No fault tolerance or error correction scheme has been proposed for this architecture, and thermal and ambient light noise at the photodetector stage would need to be characterized before any serious performance claim could be defended. The virtual spacetime language used throughout this document is retained deliberately for accessibility to a general audience, and this document repeats for the sake of the record that this language does not correspond to any claim about quantum fields, quantized spacetime, or physical superposition, and should not be cited as such. 9. Conclusion. A pair of LED arrays facing one another with mutual emission and detection produces a recursive optical feedback structure whose geometry and delay behavior are derived consequences of ordinary classical electrodynamics and closed-loop imaging feedback, requiring no new physics. Labeling recursion depth and frame delay as a virtual spatial and temporal coordinate system is a reasonable descriptive convenience and is retained in this document for that reason alone. The claim that this architecture computes at reduced energetic cost because it uses light rather than electrical bit flipping is excluded once the full detection and readout cycle is accounted for under Landauer's principle, since the dissipation is relocated rather than eliminated. A narrower efficiency claim, resting on reduced operation count for specific problems that map well onto the recursion geometry, remains outstanding and is identified here as the correct direction for further work, together with the direct energy audit experiment described above as the most important next empirical step.